Hello, and it's that time once again for some physics solutions, A-level style. We've gone for this time from the 2011 summer exam. Still in the AS1. I'm actually just going for the next question in this one, question 4. And this one is all about moments. So here we go. Question 4, and this is what it says. The moment of force about a point is defined as the magnitude of the force multiplied by the perpendicular distance from the line of action of the force to the point. So figure 4.1 shows a force acting to create a moment about the point P. So here's a force, here's a point P, and part 1 says state the directional sense of the moment caused by the force F. This can be one of two things. It can be a clockwise moment or it can be an anti-clockwise moment. So the moment is occurring about this point. So if our force is acting in this direction, it's going to cause a rotation in this direction. So it is of course then going to be anti-clockwise. So write that in, anti-clockwise. Okay, and then underneath that is our next part, and this is what it says. It says, show clearly what is meant by perpendicular distance from the line of action of the force to point P. Label the distance D. So we're looking for this perpendicular distance. Perpendicular meaning at right angles from the line of action of the force to point P. So what I'm going to do is extend that line P, or the line F. Okay, I'm going to extend that back a bit. So it's the line of action there. Point P at right angles to that will be something like this. And that's supposed to be a right angle in there. And I wanted us to mention that that is our distance D. So from there to there, it's D. Let's jump over then to part B of this. We have a monkey of mass 24 kilograms hanging from a branch of a tree at a point 3.5 meters from where the branch connects to the trunk of the tree. The branch is massive, 180 kilograms, and its center of gravity is 1.3 meters from the tree. Figure 4.2 shows a diagram representing the tree trunk and the branch. Complete the diagram by drawing arrows at the appropriate positions on figure 4.2 to represent the weight of the branch and the monkey. Label the arrows with the magnitude of the forces. So 2 marks here. One is for drawing an arrow that represents the weight, and the other mark is for drawing an arrow that represents, the first one was the weight of the branch, the second one is the weight of the monkey. It wants the magnitude of the forces as well. So of course our weight of the monkey is going to be 3.5 meters from the contact point, so roughly about here. So the blue one is for the monkey weight, and the monkey's weight of the monkey is equal to its mass times g. So that's going to be 24 times 9.81. So stick that in the calculator. So it's 235 newtons. Now next up is the weight of the branch, and it is a mass of 180 kilograms, and its center of gravity is 1.3 meters from the tree. So let's just draw that in a different color. 1.3 meters, so roughly about here. And again, this is the weight then of the branch. It is going to be again m times g, but this time 180 times 9.81. Which is 1766. 1766. I've rounded that up. Now, newtons. Moving on to part 2, we'll have the branch will snap off the tree if the moment about the trunk exceeds 4,020 newton meters. The second monkey of mass 29 kilograms starts to walk from the trunk along the same branch, assuming that the branch does not bend before it snaps. Calculate the distance along the branch the monkey will reach before the branch snaps off. So we've got another monkey who's jumping onto this branch and is going to wander this way. Once it gets to this size of a moment, then the thing will break here. So we're trying to find where along here will the monkey be whenever it gets to this point, this 4020 Newton meters. So the sum of all three of the moments will then equal the 4020 Newton meters. So let's take the two moments separately and add them together. So our first moment is going to be that of the first monkey. So it's going to be the force 235 times its distance from the pivot, which is 3.5, and then we're going to add that to the branch and its moment. So its force is 1766 times its distance, which is 1.3, and then our third one, which is the second monkey, it is going to be, well, we need to do 29 times, first of all, the 9.81 to get the force, and then times, well, what we're trying to find is that distance that it goes along. So all of those three can't exceed the 4020, so we'll just put that equal to equals 4020. So using a calculator, just multiply out these, add them together, leave in the D, and then rearrange. The first one is 823 plus 2296 plus 285D. That's still equal to 4020. So 285D is equal to, just bring those others over to the other side, 901. Last step then is, well, what's D going to be? It's equal to 3.2 meters. 0.2. Just to finish with then, part 3, if the branch had started to bend downwards as the monkey walked along it, explain why it would have been able to walk further along the branch before it snapped. Let's look again at the diagram. I'm going to draw in the bending branch, and as the branch bends here, these forces are actually getting closer to the turning point. Their perpendicular distance is getting smaller, so that then means that the moment, the turning effect of these forces is also going to get smaller. So a bigger turn effect from the second monkey is then needed to get our 4020 Newton meters. So just put that in at the bottom there, that as it bends, perpendicular distance to the forces is getting smaller, reducing the turning effect. Ooh. There we go. Alright, now there's our solutions, and there's our mark scheme. Tick.